Okay, let's continue where we left off. Hopefully finish functionality today and start the enzymes lecture. But the exam is next week, right? I am almost 100% sure I won't finish enzymes today. So which means they won't be on the test. One less topic to worry about. So the test will be on everything up until finishing up this lecture today, the functionality. And then enzymes will be part of the second exam. Okay, with that, let's, like always, start with recap questions to build up where we left off and move on. Okay, we talked about protein-water interactions. And then we talked about 3 different categories of protein-water interactions. So what were they? Physically entrapped water, okay, that is one category, and would be entrapped within the 3-dimensional structure of the protein, as well as the 3-dimensional structure of a protein matrix. What else? Bound water. So the chemically bound water that interacts closely via hydrogen bonding and van der Waals with the protein functional groups. And one more? Yeah, or hydrodynamic water or free water that is free-flowing, available for chemical reactions, and loosely interacting with water forms the multi-layer after the monolayer is formed. Okay, good. Which type of amino acids interact the most with water? So types, you have the charged. So you have the charged and then the polar and then the non-polar follows. Do you remember that equation? You have the function of all the different amino acid interaction with water. So the water interacts the most with charged amino acids, then polar, and they do interact with non-polar, but to the lowest extent. So what's the difference again between water binding and water holding capacity? So what is water binding capacity? I think Sonia is the best one that can answer this question.
Avoiding eye contact.
Huh? What's that?
I avoided eye contact.
I know.
No. Water binding is the amount of bound water that can be held by the protein, but water holding capacity is the amount of water that can be held in the 3D matrix after force has been applied.
Yeah, and after a gel is formed and a gravitational force has been applied, then you can determine how much water was retained in the matrix based on how much water was separated from the matrix. That's the water holding. The water binding is the amount of water. You start with a dry powder of protein and you start adding gradually water, and then you determine how much water get bound to the protein and will not separate when you centrifuge. So, what's the impact of pH on solubility? So think about the solubility curves we shown last time. So at which pH the protein would be most soluble?
Equal to the PI?
Most soluble or least soluble when it's at the PI? At the PI you don't have charge, so it would be the least soluble. And which pH would be the most soluble? Is it the alkali pH or the acidic pH? Alkali pH. Why is that, Claire?
The hydroxyl groups and the sulfide groups are
Ionized. Yep. So the sulfide groups and hydroxyl groups are ionized at alkali. Then you will have even more solubility at alkaline pH than at acidic pH. What about salt? Impact of salt on solubility.
I think the more we add salt, the less soluble because like more charges are there, they go freeze and
Before you add so much salt, and you're right, yeah, shielding of starch and breaking of electrostatic interaction within the protein itself, because of there's a lot of salt, and salt competes with water, and then the protein denatures at high salt concentration, and then you will have hydrophobic interactions and reduced solubility. But before that, for some proteins at certain salt concentration, what do you get? Salting in effect. So by salting in, that means you're adding some charge load on the protein that enhances water salt interactions. But the impact of salt on the protein is different based on the type of the protein and the type of salt. We showed some figures around different salts and their impact on solubility. What's so unique about whey protein in terms of solubility? It doesn't act like other proteins.
Has more hydrophilic surface, so even at its like PI,
Yeah.
it's still somewhat more soluble than other.
Not somewhat. Still soluble at the PI unless you heat it. So whey protein is unique in that sense because it's very hydrophilic on the surface. It's a globular compact protein. So even when there's no net charge, there's a lot of hydrophilicity on the surface, a lot of interaction with water, it remains soluble. Heat it beyond its denaturation temperature, then it'll open up. And when there is no net charge, hydrophobic interactions dominate between protein-protein molecules, and then polymerization and loss of solubility at the PI. How does denaturation impact solubility? So when the protein denatures, does solubility increase or decrease? Decreases. And it's mostly because once the protein is denatured, and depending on factors such as heat, concentration of the protein, and pH, you might wind up having polymerization. And if that happens, then solubility is decreased.
So,
Yeah?
is there, I just want to make sure, so if there's some partial denaturation, could that lead to any increase in solubility before it drops off? Or
Yes, so increase in solubility is not due to partial denaturation per se, it's due to heat. So when you heat the protein solution a little bit, 40 or 50 degrees C, then you have enhanced hydrodynamic interaction between water and the protein, so you have better solubility. But once you hit the denaturation temperature, then when the hydrophobic groups are exposed with more heat and relatively high protein concentration, then you end up having polymerization. Does that make sense?
Yeah.
Okay. What are some factors that impact gelation? Protein concentration, yes. Different proteins would gel at different concentrations. So meat protein can gel as low as 1%. Gelatin can form a gel as low as 1%, whereas whey protein you need about 10%. Soy protein you need 15%. So it really depends on the protein structure and how much it can form a gel. All right, what other factors? Yeah, what did you say? pH. At the isoelectric point, your gel is gritty because you will have more aggregates rather than a nice three-dimensional texture. When the pH is close to the PI but not at the PI, as it goes away from the PI, you start having a transparent and strong gel. But if it goes too extreme, high pH or low pH, what happens? What happens when you have extreme pH? Do you form a gel? No, you don't form a gel. Because again, gel is a matrix that is based on a balance of interaction between water and protein and protein and protein. So you need to have a balanced interaction between water, protein, and protein. Other than pH, salt. Same with the pH and salting in, salting out effect. A little bit of salt aids in the formation of a gel. Too much salt, you get shielding of charge, grittiness, not a good texture gel. Let's see. Do you need the protein to be denatured? Yes. So we need, in most cases, to denature the protein to induce protein-protein interactions. Okay. What about the rate of heating? Do you remember what we talked about?
A high rate of heating will cause the protein to aggregate, and then the slow heating will cause a gel.
Yes, so high rates, so like boiling, for example, you're going above the denaturation temperature, but you're heating way higher than the denaturation temperature, so the protein denatures very fast and start to aggregate very fast rather than come together slowly and form a nice three-dimensional matrix and entrap water. So the rate is very important. I would say another, what if you have enzymes in the system?
Enzymes can hydrolyze the proteins and then they won't form a gel.
Okay, so if the hydrolysis is excessive, that you end up with very small molecular weight, less than 20 kilodalton for the most part, then yes, you don't have a gel form. But sometimes partial hydrolysis actually aids in the formation of gel by exposing certain hydrophobic groups that would promote protein-protein interactions. So limited hydrolysis would be good, but excessive hydrolysis would be detrimental for the gel formation. The other important factor is we want the protein to denature, so different proteins denature at different times. So depending on the protein matrix we have, you need to reach a certain temperature in order for it to denature. So let's say if you heat whey protein at 70 or 75 degrees, you will eventually form thermally induced gel, but if you heat soy protein at 70, 75 degrees C, it's not going to gel for you. It really needs to reach this denaturation temperature for the protein to denature and then a gel to start forming. So we talked about reversible and irreversible gelation. Can you give an example of a reversible gel we talked about last time? Gelatin. So you start with collagen. Collagen is highly stabilized by hydrogen bonding. And then when you heat it, so the hydrogen bonding will break because hydrogen bonding are destabilized by heat. And then when it cools down, it reforms slowly into a gel. So when you cool it, it will form a gel, again stabilized mostly by hydrogen bonding. But heat that gel again, you are going to break those hydrogen bonding again and solubilize the protein. So that's a reversible form of a gel. Irreversible, it happens when you have high degree of hydrophobicity in your protein and high amount of sulfide groups. So, for example, egg proteins. So egg proteins will form a gel and it's irreversible. It's highly hydrophobic and it has a lot of sulfide groups. So once disulfide linkages are formed or strong hydrophobic interactions are formed, they become irreversible gel. Okay. Any questions before moving with the next topic? Yeah.
Sorry, can you repeat the last thing about the reversible gels and sulfide groups?
Yes. So irreversible gels are formed when you have a protein that are high in hydrophobicity, so a high percentage of hydrophobic groups and high percentage of sulfide group. So once sulfide groups are there, disulfide interchange occur at high temperature, forming disulfide linkages. These are irreversible once they're formed. Additionally, strong hydrophobic interactions will also result in irreversible polymerization and gel formation. Okay, any other questions about last week's lecture that you'd like me to go over? Okay, I'm still hoping one time you come with a bunch of questions and we have a discussion one day, maybe next day, maybe next week.
During the exam.
Huh?
I said next week during the exam.
Well, the exam is 1 hour. After the exam, we'll continue with lecture. Ah. Yep. That's when you have 2 lectures in a row. All right. So moving from protein-water-protein interactions, we move into surface activity, which is interactions at the interface. So surface activity relates mostly to the functionality, emulsion functionality and foaming functionality. So we start off whether it's an emulsion or foam, it's a dispersed system. So we have 2 different densities, so 2 immiscible phases, and you need some sort of work to get them to disperse with each other. And once you remove the work, so if you are homogenizing and you're applying some shear, so you can mix oil and water, but let it sit. Due to surface tension between oil and water, they're going to separate. With the oil, lower density will go to the top, and water with higher density will go to the bottom. So in order for the emulsion or foam to stabilize for a certain period of time, you need some agent to help it stabilize. So terminology, so you have the dispersing phase and you have the dispersed phase. So the dispersing phase is your continuous phase, which could be, in case of emulsion, could be your fat or the water. And the dispersed phase, in case if it's a, let's say it's a butter, your dispersed phase would be your water. Whereas oil and water emulsion, your dispersed phase would be oil. Or if it's a foam, your dispersed phase is air. You cannot have air and dispersed water. So usually it is air that is dispersed either in a fat or an aqueous system. So the dispersed phase, if it's a liquid, it's an emulsion, and if it's a gas, it's a foam, obviously. So the stabilizing agent, which in this case is our protein, once you put the protein in solution in water, let's say, and then you start adding your oil and you're homogenizing to mix the 2 phases, then the protein starts moving to the interface. It moves to the interface, and by entropy driven mechanism, it unfolds and it orients its hydrophobic groups to the fat and hydrophilic groups to the aqueous. So, and then the protein starts forming kind of a gel-like film around the dispersed phase. So the protein moves to the interface, unfolds, and start forming polymerization and forming a thin film around your dispersed phase. Once the protein is denatured, obviously, then you will form an interaction between the next in close proximity protein next to it. And then you form that matrix, and the film capture the oil droplet or the water droplet. So like I said, so you have 2 phases, and then you need to apply certain work to disperse it, to break the particles into small particles, and the smaller the particle, the better. We'll talk about stability based on particle size later on. Once these particles are broken apart, if you have protein in solution, the protein will take place at the interface and, like I said, unfold and form polymerization around the oil or water droplet. And here's just demonstrating that the hydrophilic end will orient itself to the water, hydrophobic end or lipophilic end, the same thing, will orient itself to the oil. So here's the work effect or the homogenization effect. So the homogenization will increase surface area. So it will make droplets smaller, by droplets being smaller, you will have higher surface area. So the work, so the more tension you have, the more work you need to apply in order to homogenize and break those droplets into smaller droplets, and then you will have a greater change in surface area. The surface area will increase. And then the additives, usually such as lecithin, for example, or mono or diacylglycerols, will be your surfactants that would stabilize, or you would have the protein that will act as a stabilizing agent. So here's a diagram that illustrates the impact of surface hydrophobicity on forming a film around your droplet. So in this example, so the black spot is the hydrophobic residues or groups, and then the transparent, that means hydrophilic. So if you have a protein with a lot of hydrophilicity on the surface, there will be no adsorption at the interface. None. Okay? Because you don't have any hydrophobic residue to orient themselves to the lipid compartment. However, if you have mostly hydrophilic, but you do have some hydrophobic on the surface, you will have moderate absorption. You will have some absorption, but not a lot. Again, when I say adsorption, it means adsorption at the interface between oil and water. If you have a good balance between hydrophilic and hydrophobic, you will have very strong adsorption. This is a really surface active protein. So sometimes you would hear the term surface active. That means it has an excellent balance of hydrophobic to hydrophilic groups on the surface, then you will have the best surface activity. This diagram illustrates the mechanism, what happens once the homogenization is applied in the presence of protein in solution. So depending on the surface activity of that protein, it will move at a certain speed to the interface. It will be very fast. If it has excellent balance, it will move very fast. It will flex, unfold, and change orientation, and then start aggregating to form a film around your droplet. So this is the mechanism. Going to the interface, first step, unfolding and flexing, orienting the hydrophilic and hydrophobic residues to the appropriate phase. Then because it's unfolded now, starts aggregating with another protein polymer and start forming that film around the droplet. So there are several factors that impact emulsification. You can stop me anytime and ask questions. Just reminding you.
So the interface that you're talking about, is that just like the droplets interface?
The interface of the oil with water. So when you homogenize,
Okay.
you're breaking the oil into droplets. So now you have surface area.
So you're talking about...
So that surface is the interface between the water and the oil. Or it's the other way around. If the oil is a dispersing phase, then the water will be the droplet. Yep. Okay. So there are several factors that impact emulsifying properties. So you have the protein characteristics. We call them intrinsic factors. Surface hydrophobicity. This is important that we illustrated in the figure before. And flexibility, how flexible that protein is to unfold and orient its different components to the different phases. So if you have a protein that is stabilized by disulfide linkages, it's a very rigid protein. It's not very flexible unless you add a reducing agent and break the disulfide bonds. Okay? So this is what I mean by flexibility. The protein needs to be flexible so that it can orient the different components to the different phases. Charge. Again, everything is balance in life, and so is balance in functionality. So if you have a lot of negative charge, you won't be forming those aggregates around your oil. There will be a lot of repulsion. But if there is no charge at all, what's going to happen is the opposite effect. And that's where the trick is of balance. So if you have no charge, yeah, you will form an aggregate film around your droplet. But then there is another droplet in the proximity and another droplet in the proximity. So if there is no charge at all, if you are trying to form an emulsion at the isoelectric point, what's going to happen, you think? So you formed the emulsion, perfect, you have good emulsifying capacity, but what do you think is going to happen if you don't have charges? Flocculation. So these are going to come together, going to flocculate, and then they're going to coalesce into one big drop. So it's important to have some charge so that you don't have the flocculation, but not a lot of charge, otherwise you won't form the film around your droplet.
Is this the same as like fatting out?
Yeah, creaming.
Okay.
Yeah, fatting out is creaming, yeah.
Okay.
Yeah. Yeah, because once you have this coalescence, you will have another coalescence, and then it becomes a big one, and then due to difference in density and increase in tension, then you will have cream separated from your liquid, phase separation. Solubility. I mean, like I said earlier when we talk about solubility, it's important for anything. If your protein is not soluble, it's not going to interact with water. Period. Not going to function. Primary structure as well as conformation. So by primary structure is the amino acid composition and sequence basically, and that dictates conformation or molecular configuration. So due to the composition, you can have a flexible random coil proteins such as caseinates or caseins. They're open structure, they don't have secondary structure, they're random coil, they're very amphiphilic, and because they're open structure, they take a lot of space, so one molecule takes a lot of space compared to a globular protein that could be less flexible due to disulfide linkages. It could, and it's compact, so it occupies less space at the interface. Now, in both cases, you have pros and cons. Do I have it here? Yeah, I have it here, so I can't ask the question. So the pros for flexible is more surface active. It goes to the interface quicker. It forms the film quicker. It's more surface active. But like I said, since it is an open structure, the film is composed of less number or amount of molecules because it's large, so it occupies a lot of space. Then you end up forming a thinner film because you don't have as much space around your molecule to fill it with proteins. So it would be a thin film. Whereas globular, it's not. It will come to the interface not as surface active. The emulsification capacity might be low, but a lot of it, because of it occupies small area, a lot of it are going to form around the droplet, forming a thicker film because you have more molecules around the droplet. So now you have better stability. Thicker film imparts better stability. So where do you draw the line? You want more capacity or do you want more stability? Or do you want both? Maybe we combine proteins together to get optimal effect. Okay. Denaturation is important, especially in the case of globular proteins. If you want them to be to get to the interface, and form an aggregate around the droplet, you have to partially denature them. Of course, like anything, there are effects of extrinsic factor, the environmental factors, temperature, pH, and salt. So of course, pH and salt contribute to the charge and the balance of charged and uncharged groups. Temperature, it impacts denaturation and stability after that. And then homogenization, level of homogenization you apply. So what's the pressure of homogenization? Is it going to be low or high? The higher the pressure, the smaller the droplets. And then presence of other surfactants or small molecular weight stabilizers, such as the lecithin. When you have small molecular weight surfactant compared to the protein, they're going to displace the protein on the interface. Because they're smaller, they're more surface active, so they will displace your protein. So kind of compete with the protein for the surface. Okay.
Potentially cause issues with then the protein being free.
Yeah, and stability.
Yeah, and then they would like precipitate out.
Precipitate out, or now the film is not as thick as it would be if you had protein, and it won't be as stable. Okay. So keeping all the intrinsic and extrinsic factors in mind, then what contributes to the emulsion is the rate of adsorption, how fast the protein gets to the interface, amount of protein adsorbed, how thick the film is going to form, how much flexibility the protein is going to undergo to rearrange at the interface, and how much of the tension is going to be reduced. The tension between the two phases, that is. And the ability of the protein to form a cohesive protein layer around the molecule. So the intrinsic and extrinsic factors lead to these effects, basically. So, other than forming the emulsion, which has to do with the emulsion capacity and surface activity, you have the stabilization of the emulsion. So, the emulsion gets destabilized by, creaming out, which is a function of, like I said here, fluctuation, coalescence, and then phase separation. And then you will end up having either creaming or sedimentation. Seriously now? Should I pick up?
Yes.
Hello? Who? Okay.
Who are they looking for?
Is that a wrong number?
Annie. Wrong number. Well, we were getting bored here from emulsions. Okay. So, in addition to the surface rheological properties of the protein, basically, that allows the formation of the film and so forth and so on, you have the droplet size. The smaller the droplet, the higher is the stability of your emulsion. The density difference, the larger the density difference, the lower is the stability of your emulsion. So that means you'll have higher tension when you have a high difference in density. And then the viscosity of the continuous phase. So sometimes you increase the viscosity of the continuous phase, let's say by starch or sugar or even protein that remains soluble. If you have that contributes to viscosity. So the more viscous your continuous phase is, the more stable your emulsion is going to be. And here's the illustration of it in an equation. I think there's kind of different order from what you have in your slides. But here's the rate of creaming. The R stands for the radius of your droplet. And then the G is the gravitational force. The delta P is the difference in density, and the mu is the viscosity of your continuous phase. So, for example, mu is in the denominator. So that means that the higher viscosity, the lower is the rate. So the rate is not high. Okay, and then the higher the difference in density, the higher is the rate of separation. The higher the gravitational force, the higher the rate of separation. The smaller the radius, I mean the smaller the droplet size, the smaller is the rate of separation. Okay, so this puts everything we said earlier on the previous slide in an equation. Another important point is once the emulsion is formed and the protein is on the surface forming a film, electrostatic charge and steric hindrance of the protein. So the electrostatic charge and steric hindrance of the protein. So anything that drives these droplets apart. Because you have the hydrophilic groups are oriented, let's say, towards the water. Hydrophilic group oriented towards the water, so they're going to repel each other, hopefully. And then if they're bulky, then there will be steric hindrance and they will repel each other. So proteins that have good gelling ability will form strong viscoelastic film because they can gel, they can aggregate and form a film around your droplet. And the dissolved proteins add to the viscosity of the dispersing phase and elongate the stability of the emulsion. This is Sonia's favorite functionality test. Huh? Yeah. Pretty much. Okay, so usually to determine functional emulsification property, we look at two things. We look at emulsion capacity and we look at emulsion stability. So emulsion capacity has to do with the surface activity and how much the protein is able to emulsify oil. Okay, so the definition is the amount of oil or the quantity of oil a certain amount of protein can emulsify. Usually it's a measure of milliliter of oil per 1 gram of protein. So the way you do that is you have oil in a titrator, a large titrator, and the oil you add to it Sudan red colorant to make it pink so you can visibly see the emulsion. And then you will have your protein solution. So the protein solution, oftentimes it's 1% protein, but sometimes 1% protein is not enough to form an emulsion. Sometimes you need 2% protein, but too much of a concentration of protein, what happens, Sonia?
Protein interaction.
And then you don't form the emulsion. Rather than having protein-fat interaction and protein-water interaction, you end up having more protein-protein interaction, and they won't emulsify. And that Sonia experienced firsthand. Many times. So the concentration of your protein solution is very critical in order to do accurate measurements. But let's say we determined experimentally that 1% protein solution is good. So you prepare your 1% protein solution, and then you have your titrator with the oil, and then you have a homogenizer, a specific shaft blade size and dimensions. And then you insert that blade in your solution and you start adding oil gradually, so it's like titration, and then the shaft is working. You are homogenizing at the same time as you're adding the oil. So you form an emulsion. So this is what a smooth emulsion looks like. So you continue adding oil until the emulsion breaks. And it looks very different. You'll see that the oil separates, and then you see you have aggregates, and you even hear a different sound of your shaft. So that you'll have different sound. You did that too. You see you nodding. Yeah. So you remember that you start hearing a significantly different sound. But anyway, so we call this inversion of the emulsion. As soon as your emulsion breaks or inverts, you stop titrating and you take the volume difference. You see how much volume was titrated into that 0.1 normal. 1%, why did I say 0.1 normal? 1% protein solution. And then you do the math to get this emulsion capacity in the form of milliliter of oil per gram of protein. Emulsion stability, it's a quick measure. There's a lab procedure that you can quickly predict a creaming rate. So obviously emulsion that is prepared for industry, you don't want it to break in minutes, right? It's a long process, but you can predict if you're comparing different proteins to each other, you can run an experimental procedure to predict the emulsification stability of a particular protein. So you measure breakage of emulsion over time, but the quick way to do it is using a spectrophotometric method of measuring turbidity. So you prepare your protein solutions, and then also you use a homogenizer to homogenize oil with the protein. You form your emulsion, and then you take an aliquot of it, you put SDS so that you avoid creaming while you're doing the measurements, and then you measure absorbance at time 0, and then you measure absorbance at time 10 minutes, or was it 15 minutes? 10 minutes, and the equation here should say 10 minutes then. And then there's an equation to determine emulsification stability by using the absorbance values, and then the value would be in minutes. So you will get a quick estimate or a rough estimate of emulsification stability. Okay. So interaction of protein and air. So in this case, it's foaming. So the principle, I would say, is similar to the emulsification. Again, you have surface tension, obviously, between air and the aqueous. And then air is actually injected or whipped into your solution. So either you inject the air or you whip it in. And with the whipping process, you are inducing the protein to move to the interface between the air and the liquid. And then the protein orient its groups. If you have water, then the aqueous, the hydrophilic will orient to the aqueous, and then the hydrophobic will orient to the air bubbles. Again, the protein, the same way, will form a film around your air and then stabilize the air there. Now, while the mechanism is very similar to emulsion, I mean, I had a comment there that I deleted it. Not every emulsifier is a good foaming. You might have an emulsifier that is a good foam, but the mechanism is so complex, even Fenema was not able to explain it. Yeah. So it really is a complex mechanism, but again, the principle is the same. Protein unfolds, goes to the surface, unfolds, form a film around the bubble. Yeah, this is what I said, and I said that already. And a lot of food products are actually foam. So cake, meringues, whipped cream, they're all foam. So again, you have two, let's say you have your droplets with bubbles, we call them, or not droplets in this case, bubbles, that are stabilized by your protein film. So you have something called disjoining pressure. That means the electrostatic repulsion and hindrance between the proteins here will prevent the bubbles from coalescing, from coming together. Now, another mechanism, you have the thinning of the liquid film. That means by capillary forces, the liquid might drain out to the borders, and if that happens, the bubbles will coalesce and form big bubbles, and then the foam breaks. So one way of reducing this is, again, increasing the viscosity of the dispersing phase. Okay.
Is it possible that you could increase the viscosity of the aqueous phase too much? And then it would like collapse the bubbles?
How would it collapse if the viscosity is too high? Think about cake. So the solid matrix of the cake actually fix the foam in place. Yeah.
So is that part of what contributes to making a heat stable foam? Sort of like
Yeah, when your starch gelatinizes, for example, and the protein also gel, then that traps your air bubbles. Yeah, good. Let's see, did I larger net charge protein? Yeah, so these characteristics of the protein, when you have certain amount of charge and certain amount of hydrophilic amino acids, this will aid in the disjoining pressure and avoiding coalescence of the bubbles. Okay. So measurement of foam, again, you have two parameters, foaming capacity and foaming stability. So foam capacity is often either measured by measuring just the foam volume or overrun, or you can actually measure foam capacity by relative to the amount of protein. So milliliter of foam generated by 1 gram of protein. So you can do that either way. So if you do the overrun, this is your famous equation of the overrun. So you generate a foam. If the protein is able to form good foam, that is, you whip it until all of the liquid solution turns into foam. And then you measure the overrun. The overrun is the volume of the foam minus the initial liquid over the initial liquid. Volume of the foam, that is the total volume after you induce the formation of foam. But sometimes, no matter how much you whip that protein, it won't all foam. Right, Sonia? So in this case, you just measure the amount of the volume of the foam itself, and then you relate that to the amount of protein that you have. So you won't measure the overrun. Foam stability is over time. You monitor the release of liquid from the foam or the drop in the foam volume, either or. So basically, milliliter of foam remaining after a set period of time, or the free liquid generated after a set period of time. Again, these measures are usually are experimental measures to compare functionality of different proteins to each other, or if you modified the protein, you can see what happens to functionality. This is really prediction to what could happen in real life. And it's only prediction because in real life, your food matrix is so complex and so many different factors impact foam stability and foam capacity. Any questions about foam or emulsion?
So overrun is defined as the change in volume.
Yeah, the additional change in the additional volume compared to the original. So let's say you started with 100 ml and then you ended up with 200 ml. then you have 100% overrun,
Okay.
right? Yeah. So 200 minus 100 over 100, then it's just 100%. Okay. So, with that, where are we on the map? So, I think we did, of course, we looked at all the intrinsic factors, we talked about functionality, how structure impacts functionality, and then we talked about a lot of extrinsic factors. We haven't done protein modification yet, that's the last component. And then later on we'll do different proteins from different sources. There will be a whole segment on that. But before we go into different proteins from different sources, it's important to talk about enzymes. So we will kind of have a break, talk about enzymes, and we will have actual break right now. So you can take 5 minutes.
Same cycle.
So like the one I got after 2 hours. So 120 the second one, 9 something. And then but just on starch
No, I'm laughing at what she said.
okay. Yeah, my first one. So my
I don't know
first
why
one,
she's
like
laughing.
the one after 20 minutes is like 25.
On the why is
25 seconds.
Yeah.
And the one you got after 2 hours is
lots of movement.
No.
overnight is 1 second. But usually the overnight was
I know about the chips, but.
Right. Yeah, I saw it. They were good.
just
Oh, oh.
Like I'm so angry when I
on both. So I feel like
Oh, both sample. And then,
yeah, so the one I
The music store opening thing that you're going to,
both samples got
right
lower
next to where I live.
after.
Wait,
Well,
you
it's
live
down
there?
the street. Well,
That means I live close to you.
where do you live?
I live on 11.
On what?
11.
Oh, I live over
I
two.
haven't checked the
Oh.
other
So like,
on
so
Saturday.
you're close to 335, I'm close to 280.
Oh.
So it's like
in the middle.
It's really
It's kind of weird.
I didn't realize you lived there.
Yeah. I want to go really badly because on the Saturday at 4, they have a giveaway.
Well,
For-
for a clarinet, right?
Yeah, it's a $4,500 clarinet
Dang.
from a buffet. And so that would like greatly improve the current clarinet that I have right now.
Nice.
The thing is, I have a musical rehearsal in Chaska that day.
Oh, geez,
So I'm
that's
like,
far.
I'm leaving early, like an hour and a half early from this rehearsal. That's
So I can get a better instrument.
potentially. I'm gonna go there. My hopes will be low because.
Yeah. I was just really excited that it was going to be so close because I was like,
Yeah. I can walk to it.
Yeah, I need to take my violin in because I haven't taken it anywhere like since I moved here. It's terrible, but oh well. And I was like, oh, there's music stuff. Like I probably can't bring it there because it's even more woodwind focused, but it'll still be nice. Okay, I was gonna say I did see some very pretty new bands and stuff. I
Yeah.
wanted to get some here. I know they're not Parisian, but
Just that issue some meal. And then wait by the time you send them back and
I think we had.
Okay. We were just.
Or just,
It's like,
just grab the one there.
But in my work, I will include the overnight on the graph.
Just make 2 grabs. Don't not all together.
do you know which building? It's your mom. It's an offline.
It's not doing that.
Do we have everybody back? Okay. Let's get started with enzymes. Some of you, this might be a refresher or combination of certain courses where you covered enzymes, and we will have some examples related to food applications. Okay. Which of this is true? Hmm? What? Other? Just A. Huh?
Wait, just say.
Just A? Just A? Well. Well, I'm going to say B and C are wrong. A, we will discuss that. So B, enzymes are not necessarily all made up of amino acids. So you could have other groups attached to it. So you have combination of scenarios. You have apoenzyme, holoenzyme, and an enzyme. So apoenzyme is an enzyme that is not active. So that means it needs a certain cofactor or a coenzyme. Different sources label cofactors and coenzyme differently, but coenzyme is a cofactor. Okay. Some references say cofactors are inorganic groups that are linked to the protein. But anyway, we'll talk about cofactors and coenzymes later on. But what I want to say here that an enzyme might not be active unless a cofactor is linked to it. Then it becomes a holoenzyme or a complete enzyme or active enzyme, and then the substrate will bind and a product will be formed. But that doesn't mean that every enzyme requires a cofactor. Okay? Some enzymes do not require a cofactor and function as such. Other enzymes require cofactors. And some cofactors bind strongly to the enzyme and they bind via covalent interactions and remain with the enzyme. Other cofactors bind loosely, and coenzymes are actually the cofactors that bind loosely. We'll talk more about that. So B is incorrect, and C is the opposite really. Enzymes reduce activation energy very much. So the rate of the reaction is increased. So they are catalysts, right? So, all right, everybody's favorite subject. Yes, it keeps coming back. There's no end. Okay, so you love kinetics, right? We're going to talk about enzyme kinetics quite a bit.
Just B.
Just B. Yep. Right, you're right, just B. And we'll talk about why it's just B, but does anybody, well, since you answered, what's Km?
Km, it's the concentration at which V is equal to half Vm.
That's true. Km is the concentration of the substrate at which the velocity is at V max over 2, or half the maximum velocity. And well, it's Michaelis-Menten constant, and it's directly related to the affinity of the enzyme to the substrate. And we'll talk about how that is when we get to that. Okay. And we'll explain why it's B when we get to that. Okay. Let's talk about examples where enzymes are important in food systems. Where do we use them? How do we use them? Why do we use them?
Wait, I
Hmm?
Oh, okay. In cheese, rennet for curd formation.
Okay, so processing aids. Okay, what else? Processing aid is good one. Cheese production, hydrolysate production, yeah,
When you use
high
them-
fructose corn syrup production.
When you use them for meat, like tenderizing, is it like processing or?
Processing aid, tenderizing meat, yes.
Breaking down tough fibers.
Huh?
Breaking down tough fibers like meat.
For meat, like meat tenderization.
Like bromelain.
Bromelain, yeah, bromelain and papain are meat tenderizers. Yeah, so you're all listing processing aids. That's one of these boxes. Okay, what else? Yeah,
It speeds, or is this going to be a processing aid?
What?
It speeds up reactions.
it speeds up reaction for all of these. It's going to speed up reaction, but what reactions? What enzyme do we measure the activity of to test pasteurization of milk? Alkaline phosphatase. So quality, determining of quality. Alkaline phosphatase is an enzyme that is more stable than any pathogen in milk. So instead of doing a microbial testing to determine if the pasteurization, which is killing all of the pathogens, has been done correctly, instead of doing 2 days worth of microbiological testing, they test the activity of alkaline phosphatase. And if it's inactivated, that means all pathogens have been inactivated. Same for blanching. What do we test? Peroxidase, lipoxygenase are enzymes that get activated. Is a blanching procedure, is to inactivate enzymes. It's the first procedure in processing to prevent browning, let's say, or off-flavor generation during processing or storage. So they do the blanching step. Okay, what else? Food analysis. How do we use enzyme? For what? How do you determine glucose sometimes? Glucose oxidase. So determining of certain constituents of food. So when you do starch, total starch, for example. So you hydrolyze the starch. Yes, he's laughing at you. He knew that you knew it. Okay. You hydrolyze starch, you break it down all the way to glucose, and then you do an enzyme assay with glucose oxidase enzyme to determine amount of glucose. So constituents analysis, okay, using enzymes. What is present in soy that we want to make sure that it's inactivated? Trypsin inhibitor. How do we make sure it's inactivated? We have to test the presence of trypsin inhibitor after processing, and you test that by having trypsin as an enzyme react with an extract from soy and to see if that trypsin was inhibited or not. If it's not inhibited, that means a trypsin inhibitor was inactivated. Sometimes, let's say for cheese production, you want to use rennet enzyme. So you want to know how much rennet you need to add to have a certain amount of curd produced in a certain amount of time. So you need to determine the activity of rennet and the kinetics of rennet in order to determine how much to add of it and what would be the conditions of the reaction and how long it would take to generate the curd. So measuring activity of certain enzymes that are needed as a processing aid. Okay, one last one is waste management. So if you have a waste stream that is either high in protein or fat or carbohydrate, and it's going to go and clog the system, so they put enzyme treatment to break it down so that it can be managed. So a lot of different applications for enzymes in food system, and because of that, we need to understand how they function and learn about enzyme kinetics. In enzyme kinetics, we learn about the affinity of an enzyme to the substrate so that we can choose the right enzyme for the right application, or understand what would inhibit the enzyme if we don't want it, like polyphenol oxidase, for example, causing browning. How do we prevent the browning reaction? We do that by understanding how the enzyme function, what's optimum pH, what would be a good inhibitor. For example, how would we prevent certain enzyme from functioning, or how do we promote certain enzyme activity? So in order to be able to apply enzymes or prevent enzyme activity, we need to understand kinetics. All right. You all know this. It's fun. What's the definition of an enzyme? Xiao Chen? Do you know what an enzyme does? Simply. Huh?
Catalyzes the reaction without changing the products from them.
It speeds up the reaction. It's a catalyst. It's a biological catalyst, basically. Speeds up a chemical reaction. That is very simple term. Converting substrate to a product by lowering the activation for that reaction, the activation energy for that reaction. And it does not get consumed by the reaction. The enzyme is always released at the end of the reaction. So you start off with enzyme, reacts with substrate, you get the enzyme substrate complex, then you have the product, and the enzyme is released again to go back and continue working. Okay. Now, are enzymes proteins? Do you feel like it's a trick question? So you're not going to answer. Mostly protein. And some of them are not proteins. So some enzymes are proteins, some enzymes are not proteins. Let me tell you a story then. Let's start with stories. So, in 1920 and before that, it was generally thought as they are proteins. And then after 1920, researchers started isolating and detecting enzymes. And Willstetter is a German scientist. He isolated horseradish peroxidase to a very pure, in a very pure form in solution. So what they did is, after isolation, they found in that solution very high activity of horseradish peroxidase enzyme, but when they measured protein content, they found no protein. Then their conclusion was enzymes are not proteins. And then Sumner is an American scientist from Cornell University, isolated for the first time urease enzyme and was able to crystallize it and look at the structure and proved that it was protein. So the scientists divided, the European scientists versus the American scientists. European scientists sided with Willstetter, and of course American scientists sided with Sumner, but the debate ended when Sumner won the Nobel Prize for his discovery that, yeah, enzymes are proteins. But then after that, in the 60s, this group of scientists proposed that some RNAs act as enzymes. RNAs are not proteins. They're nucleotides. So, and then in 1981, this other scientist, Thomas Ketch, or whatever you say his name, proved that actually ribozyme, which is a form of RNA, functions as an enzyme in biological systems and catalyze certain biological reactions that occur in the cell, similar to what an enzyme, protein enzyme, would do. So now what? So, I mean, enzymes are proteins, but there are non-protein enzymes as well. But all enzymes that are related to food are protein enzymes. So we don't care about ribozymes, basically. Just want to tell you the story. But yeah, so in food applications, all enzymes we work with are proteins. In biological systems and living cells and tissues, you have ribozymes that have catalytic activity, and they're not proteins. So what did you get out of all of this?
Most are
Most are.
The ones we think about are protein.
Okay, we'll assume they're proteins and go from there. Okay, so a lot of enzymes have been separated over the years and identified and characterized, and separation was done by chromatography, all sorts of different chromatography, electrophoresis, and also the separation was based on the solubility of the enzyme and different physicochemical characteristics. Nearly over 3,000, and the number is increasing, have been purified from different matrices, plant sources mostly, fungal sources, bacterial sources, and they've been characterized in terms of structure and function. So structure, the primary sequence of the first enzyme was determined in 1960s, and from there on many other primary sequences have been elucidated by gene sequencing and mass spectrometry, and the secondary and tertiary structure identified by NMR. So a lot of work on enzymes done by biochemists, really been done to identify different enzymes, structure, and function. And they found that, like any other protein, they can be homogeneous or heterogeneous, and they range in molecular weight. Some are very small, some are huge. And also scientists are able to synthesize enzymes by PCR once the gene has been isolated. So, nomenclature. So, how do we name enzymes? So there is, for every enzyme that is registered, that means identified and functionality is known or activity is known, it has a commission number. EC, enzyme commission number. And each enzyme, or many enzymes, they have trivial names or common name, like trypsin, or papain, or pepsin, or chymotrypsin, or plasmin. These are all common names of enzymes. But a lot of time you'll hear systematic names for the enzymes that are based on the type of substrate they act upon and the type of reaction that they catalyze. So the type of reaction, you have 6 main categories for the type of reactions that enzymes catalyze. You have the oxidoreduction reaction, such as, for example, hydrogen peroxide oxidoreductase. This is the name of where you have the substrate, and what does the enzyme do? So it oxidizes and reduces hydrogen peroxide. Hydrolysis, so it's one type of reaction. So you have all of these hydrolases, proteases, for example, lipases, alpha amylases. These are all hydrolases. So that means they break bonds and take up H2O in the process, or water. Transfer. They transfer certain functional groups, transfer a phosphate group, for example, like a glucose 6-phosphotransferase, where it takes phosphate groups from ATP and put it on glucose. So that's transferase. Formation of double bond without hydrolysis. These are lyases. I don't have it written here, but so you don't have a double bond in a compound, and the presence of lyase takes a couple of groups or atoms from the molecule and generate a double bond in the process and release a functional group. It could be sometimes releasing H2O, taking OH and H, creating double bond and releasing H2O, for example. Isomerase, such as producing high fructose corn syrup, where isomerize glucose into fructose. This is isomerase. Ligation is generation of a covalent bond. Catalyze the formation of covalent bond. So these are the main reactions for enzymes, and that's where the systematic name comes from, and these are examples of a hydrolase, a transferase, and oxidoreductase. Okay, so enzyme specificity. So the enzyme has to bind stereochemically to the substrate in order for the reaction to occur. A very specific binding to what we call an active site. So every enzyme has an active site where the substrate binds. Does it bind via covalent or non-covalent? Non-covalent. So usually your interactions are via hydrophobic interactions, hydrophilic, ionic, hydrogen bonding, van der Waals, all sorts of non-covalent interaction that are very specific between the substrate binding site and then the catalysis site, which is the active site on the enzyme. So again, there's history behind the stereochemical binding. The scientist Fisher in 1894 established the lock and key theory, where not only you have stated that the enzyme forms stereochemical bond with the substrate, they also state that the binding or the active site is a rigid site. So like the lock and key theory. So it is a fixed position of the protein or enzyme where the substrate binds very specifically to the enzyme. Now, is this theory correct? No. Why? Because it was a trick question? Because the correct part of this theory, it's a stereospecific complex. The incorrect part is a rigid active site. So the actual more true theory is the induced fit theory. The induced fit theory is that depending on the conditions of the environment, in the environment, you have a certain orientation of groups in the active site that facilitates binding with the substrate or not. Okay? So the active site is not rigid. It will form a shape once the substrate binds to it, and then you have the complex, and then a product is generated. But that site is impacted by the environment. So the pH changes the ionic state of the binding site, and even the ionic state of the substrate itself at some point, depending if the substrate is impacted by charge or not. But mostly the pH impact the active site of the enzyme. Ionic strength also impact the active site, temperature, water activity. So that's why we have optimum pH, optimum ionic strength, optimum temperature, so that you have the correct chemistry of the binding site for the substrate to bind. So since we'll be talking about kinetics, we need to understand the reactions that happen when you have enzyme and substrate. You have rate constant 1, which is the rate constant for the reaction enzyme plus substrate. It generates the complex, enzyme substrate complex, which can go both ways. It can go backwards. So the K minus 1 is the constant rate for the reaction that goes backwards. And then the K2 is the rate constant for the reaction that goes to the product. Okay? So enzymes, this is probably you've seen this figure before, but this is basically illustrating that in the presence of an enzyme, your activation energy is reduced dramatically, and by that the reaction proceeds very fast. So the rate of the reaction is sometimes multiplied by a factor of 10 to the third, even 10 to the 11th times faster in the presence of enzyme. So what impacts the velocity of the enzyme reaction? Many factors. Obviously, it's directly proportional to the enzyme concentration. The higher enzyme concentration, the higher is the reaction rate, but this is not absolute. It is impacted by the substrate concentration, because if you have your substrate gets depleted, then there's no more substrate for the enzyme to convert to product, and the reaction rate slows down. But let's say the enzyme is saturated by substrate. The more you have enzyme in the system, the faster is the rate of the reaction. It's also dependent on the concentration of the substrate, as I was saying. Also the inhibitors in the system. We have several different types of inhibitors. We'll talk about that. And also cofactors. We'll talk about each one of these separately. Of course, they are affected, the reaction of the enzymes affected by pH, temperature, and ionic strength, environmental factors. Specifically for pH, so the rate of the reaction decreases by about 0.5 times when we move one pH unit from the optimum pH. Let's say the optimum pH is 7. If you have a pH of 6 or pH of 8, you are reducing the rate by half time. Same with temperature. It's the temperature also, as you deviate from the optimum by 10 degrees, you decrease the velocity by 1.4 to 2 times. So these are general terms. So we need to understand enzyme kinetics to control the rate of the enzyme catalyzed reaction. And why is this important? Why is it important to control the rates of the enzyme reaction in food applications? Wake up. Why do we care? Why am I spending time on this? Okay.
Because it could affect how long your processing takes. So if you need a specific reaction, or like you were saying earlier, the amount to add, it will affect your cost, it will affect your time.
Exactly. So from the processing perspective, we need to have the most efficient process, the least amount of enzyme or the least amount of substrate and the shortest time. So we need to understand if we're using this enzyme as a processing aid, what would be the most efficient way of using it. We need to understand the kinetics. We need to know what its Km is, its Vmax is, what inhibits it, what substrate works better with it. And at the same time, if we want to control a certain reaction, like we don't want to have browning of shrimps or browning of apples or browning of vegetables, anything. So we don't want browning. How do we control the reaction of polyphenol oxidase? We need to understand the polyphenol oxidase from different sources. Polyphenol oxidase in apple is different from polyphenol oxidase in mushrooms, is different than polyphenol oxidase in potatoes. So all will react differently, and inhibiting the reaction will be different for different sources. And it begins. All right, so let's dissect the reaction rates bit by bit. So let's look at this figure here. So here you have a certain concentration of enzyme, certain concentration of substrate, okay? And then when you start the reaction, you have a known amount of enzyme, known amount of substrate. Then you monitor the production of product over time of the reaction. So if I'm plotting product over time, this is the curve I would see if I let the reaction go long enough. If I let the reaction go long enough, this is the curve that is generated if I want to plot my data. So the first portion of the figure here is our lag phase, kinda, because here the enzyme and the substrate are binding to form the ES complex. So this is the pre-steady state. So you have K1 is the rate of the reaction. Here is the highest. This is happening. We don't have this yet, and this is not going backward as much. So we have the complex formation. After that, you have what is called steady state. So that means the rate of disappearance of ES equals the rate of appearance of ES. That means rate of appearance is this, E plus S into ES. Rate of disappearance is the combination of going into product and going backward. This is the linear portion of your figure, and that is where if you get the slope of that, that would be your initial rate of the reaction. So the slope here is your initial rate of the reaction. You see that the line plateaus as you go up. Why? Why does this happen? What?
Like it's becoming saturated, so
It's not saturated really. You
all
are
the substrates
depleting.
has been converted to the product.
Yeah, so you're depleting the substrates here. So you no longer have a steady state. Your slope is changing because now you don't have enough substrate to convert into product. Your enzyme might not be saturated with substrate anymore. So here the rate of depletion of ES will be higher than the rate of formation of ES. Okay. So that's your initial velocity from the steady state. You get your initial velocity, so that's obtained as the slope of the curve following the pre-steady state. Now, in this curve here, you would run the reaction each time with a different concentration of substrate. You increase the concentration of the substrate each time you run the reaction. then you have an initial velocity for each reaction, right? So you will have this figure here for every concentration. You take the slope at each concentration and you plot it. So you will have the velocity or the initial concentration or initial velocity against the concentration of the substrate. When you plot that, you'll get this kind of curve. So from here to here, you see linear curve, and then it plateaus almost. So what does that mean? Here at this side of the curve, your enzyme is saturated with the substrate. No matter how you increase the substrate concentration, you reach maximum rate. You cannot increase the rate of the reaction anymore based on the substrate. So it's zero order with respect to substrate. At this, because here between 12 and 16 there's no difference. So zero order, that means the reaction is not impacted by the concentration of substrate anymore. What might impact the reaction here? The enzyme concentration. So at this portion of the curve, if you increase the enzyme concentration, Vmax will increase. Okay? So here, zero order with respect to substrate, first order with respect to the enzyme. Here you have this linear curve. Here between 0 and Km, which is the concentration of the substrate at half Vmax, as you increase the concentration of substrate, your rate of the reaction increases. So here in this portion of the curve, it's first order with respect to substrate, zero order with respect to enzyme. So that's here versus zero order with respect to substrate, first order with respect to enzyme. So Vmax is the maximum velocity at a specific concentration of an enzyme and at a very large concentration of substrate. That means the enzyme is saturated with the substrate. The Michaelis-Menten is the concentration of the substrate at half Vmax. Here we go. Okay, why? Why is it always like that? All
We're
right,
gonna
so,
start putting
huh?
signs. We should put hazard signs.
Hazard sign. Proteins don't enter. All right. So Km is an indication of the relative binding affinity of the enzyme to the substrate. How is that? Why is that Km is an indication of affinity? This demonstrates that. Okay. So let's say the red substrate and the blue substrate and the same enzyme. Okay? One enzyme, two different substrate. Which of these substrate does the enzyme have higher affinity to? Which one? Huh? The red or the blue? Huh?
Red.
The red. Yes, the red. Because here at lower concentration of substrate, you have the same velocity of this concentration of substrate, which is higher. So one substrate, you needed higher concentration to reach Vmax over 2 than another substrate. So the higher the Km, the lower is the affinity of the enzyme to the substrate. Okay? That means you need more substrate to reach a certain velocity. Okay?
Can you say that again? The higher the Km?
The higher the Km, the lower is the affinity of the enzyme to the substrate, because you need more of the substrate to reach a certain rate of the reaction. Does that make sense? Lower affinity. That means more of the substrate is needed to reach a certain velocity of the reaction. So you have, the enzyme has low affinity to that substrate. You want to give it more of it to reach a certain rate. So Vmax is impacted by several factors: the substrate, enzyme concentration, obviously, pH, the environmental conditions, presence of inhibitors. Km is impacted by the nature of the enzyme and the substrate, the affinity to each other, pH, temperature, and inhibitors. So these are the factors that impact each parameter. So you have consequences for low Km. Sometimes the consequences are good, sometimes the consequences are not good, depending on the situation. So in a situation where you are producing a product using enzymes, you really want a low Km. Okay? So here in this example, you are producing 40 dextrose equivalent corn syrup using alpha amylase with a low Km. That means high binding. So the rate of the reaction at lower concentration of the substrate is high. So you're producing more per unit time. So this is good. So this is an example where your low Km is good. So if we have two enzymes that react on the same substrate, we want to choose the one that has the lower Km to our substrate. So we get more yield, more product per hour. But if the concentration of the substrate is high, it doesn't matter if you have low Km or high Km. If the concentration of substrate is not a limiting factor in our production, we don't care. So that's what I meant here. Because now the enzyme is saturated, no matter what, the Km doesn't have an impact. Bad consequence of Km is that when you do not want the action of a certain enzyme, and then you have a substrate that has low affinity or high affinity to that enzyme, then the reaction goes. For example, browning. That in this case you don't want to have low Km. So there are the adverse reactions of enzyme and then the reaction of enzyme that are desirable. So if it's desirable, you want low Km. If it's non-desirable reaction, you don't want low Km. And this is what we said about first order and zero order. And then when do we use them? So if we are to measure substrate, like I want to measure glucose, so I want to make sure I work here in this range. So I want to make sure that the solution that I prepare is a low concentration, so that if I'm looking at differences in concentrations between samples, I'm able to pick that up based on the reaction rates. So when I'm measuring substrate, I want to make sure that it's zero order with respect to the enzyme and first order with respect to the substrate. I want to make sure that the enzyme is abundant, is not the limiting factor, and substrate is limited so that any increase in substrate will cause a change in the reaction rate. The opposite is true. When I want to measure enzyme activity, I want to make sure that my reaction has abundance of substrate, that substrate is not the limiting component of my reaction. So I make sure I have enough substrate that saturate the enzyme, and then look at differences in enzyme activity as I change the concentration of my enzyme. Okay, so when I want to measure substrate, I want to work in substrate much lower than the Km. When I want to measure enzyme, I want to work in this range with substrate much greater than Km. Derivation of Michaelis-Menten equation. We need to understand how we can get to an equation that will give us or allow us to calculate Km and Vmax, which are the important kinetic parameters of enzymes. But I'm not going to start it now. The reason is it's lengthy. So I want to start and then stop and repeat next time. So I will started next time, the only downside of next time is, guess what? What? After the tests, you'll be out of it. Huh?
The test is super easy
Uh,
and, the mental capacity will still be
I
there.
will be fresh and ready for your lecture.
Yeah.
So maybe we start with the lecture before the exam?
No.
No.
We won't be paying attention to the lecture at all because we have an exam.
What?
No, wait. The reverse that.
Uh-huh.
We
Okay.
They don't care about the lecture.
You don't care about the lecture?
No, I mean.
What? Whatever you're saying is becoming worse by the second. So maybe you should stop.
I'll